Welcome to our lesson 2 for discrete mathematics, and this is in continuation with lesson 1, which is compound statement. Now, in compound statement, we have important classes now to be discussed. We have tautology, contradiction, and contingency. Let's discuss first tautology. The symbol for tautology is this one. Okay. This one, it's like a pi, the symbol for pi, but it's just rotated 90 degrees. So now, in a tautology, for all the possible combinations of your compound statement, okay, of your atomic statements rather. So for all the possible combinations of those atomic statements, the result is always true. Okay, if the result of or the truth value of that compound statement is always true, then we will call it a tautology. On the other hand, if all of the possible combinations for that compound statement is always false, then we call it contradiction. Okay, again, if I have a truth table which have variables p, q, and whatever logical connectives we use, let's say we will use conjunction and disjunction and conjunction. Okay, suppose I'll change it to 3 variables now. So now this PQ, if we have 3 variables PQR, so that means we will have 8 possible combinations. Now, if for that combinations the result is always true, then that is tautology. However, if for each combination, the result is always false, then that is contradiction. If it is not tautology nor contradiction, then that is contingency. Okay? Now let's have this example. Determine whether the compound statement is tautology, contradiction, or contingency. Now what will we do so that we can determine whether the compound statement is tautology, contradiction, and contingency? For us to be able to answer this one, we will have to create a truth table. So going back to our lesson in truth table, again, you have to identify the atomic statements, so that you can identify the variables, propositional variables, okay, those without connectives. Okay, for number 1, we only have P and Q. So that is why we have here P and Q. Then again, since we have 2 variables, we have 4 combinations. Now, in our previous discussion, I start with true, but actually we can start with false. Okay, it depends on you which value will you start. So if for this case I change it so that you will be able to know, for you to know that the combinations can change. Okay, the sequence of the combinations can change. It's still all right. Still okay. Okay, whichever you start, whichever value you start, as long as the logic is that for the rightmost part, it should change every line. Okay, for the leftmost, for the next one, the next variable, every 2. Okay, every 2 lines. So we have here the conjunction of P and Q, then Q. Now, if the conjunction of not P rather and Q, then Q. So we have this. Now let's get since only P is being negated, so we will have to get the negation, or the inverse of P, and that's true, false, false. Then these statements here in the parentheses, that's conjunction. So you have true and false is false, true and true is true, false and false is false, false and true is false. Then the whole statement, now you have um, false. If false, then true is true. If true, then true is true. If false, then true. If false, then false is true. Now, all of the possible combinations are true. That would mean that this compound statement is a tautology. So we have this final answer. Now, therefore, if not P and Q, then Q is a tautology. For number 2, we have this. I'll just erase this one. Oh, I missed it. I put a not sign here. Okay, we have P and Q. So again, we only have 2 variables here. No, 2 variables involved. So 4 combinations. Then evaluate first, no, those inside the parentheses, and then all after. So now for all the combinations, we have false. That means number 2 is a contradiction. Okay, now you have to answer numbers 3 and 4. So to guide you, number 3 is a contingency and number 4 is a tautology. Okay, so I will leave that to you to solve for or to create the truth table for numbers 3 and 4. If you are asked to evaluate, no, meaning you have to evaluate the statement first and compare it to the truth table of this statement. Let's check if both have the same answers. No? But to tell you, these are just the same. No? These two are just equal. Okay? Logical equivalence means the previous, this one. Now, when I say logical equivalence, you evaluate this and check if this is equivalent to this expression. Now, this statement, check if it is equivalent to this another compound statement. So that's logical equivalence. So they will have, for their combinations, the combination of the first compound statement, if you compare it to the combination of the second statement, the truth value will always be equal. Then they are logical equivalent. Okay, when we say logical equivalence, now we denote it with this one. No, we have an equal sign with another bar, with a third bar, or you can use this symbol. Okay, again, two statements are logically equivalent if they have the same truth value for every row of the truth table or for every combination of your variables. And since they are logically equivalent, so that would mean that they have the same value. Therefore, if you get the implication or by implication of the two statements, then that should be a tautology. Okay, same raman sila og values. So for example, compound statement A and compound statement B have the same values. So kung imo siyang i-by implication, so true gid siya pero may kay same. Kung ang isa true, ang isa if T is true, then you get the by implication. If A is true, B is true, their by implication is true. If A is false, okay, since equivalent man silang dual, then B should also have a false value ng a row or combination, and that would be true. Now, for any combinations of A, of the propositions inside A, and any combinations of the same combination of the propositional variables inside B, they should be equal. If they are equal, then they are tautology. Mao gini ang concept sa logical equivalence. They are equivalent at the same time they are tautology. Getting the by implication is a tautology. So here are some exercises. Determine whether the given statements are logically equivalent. Okay, we have if P then Q, and if not P then not Q. So here's the answer. Now, first is we will have to evaluate if P then Q. Okay. Then next we have to evaluate if not P then not Q. Now you take note that I did not put any more P and Q here since I already have uh, a reference, no, in the first table. So though you actually have to create, no, to put P and Q, but again I did not put it since I have already a reference in the first table. They are logically equivalent. That is because now we have to consider this, no, not P and not Q. So for if P and Q are false, and if not P and not Q are also false, then the result are true. Now if you check the arrows, now they have the same combinations. I'll just erase this. Now they have the same combinations of FF for the first table. Second table is also FF, and they have the same truth values. Next, if we go to FT and FT, so they have the same truth value. Now we have T for implication and the T for this contrapositive. So therefore, since they have the same truth values, no, for whichever combination, therefore they are logically equivalent. And no, and A and B, or P, if P then Q, if we get the by implication, for Y, if we get the by implication of if P then Q with not P then not Q, then this should be a tautology. Okay? This should be a tautology. So since they are logically equivalent. That's how we answer, or we evaluate whether two compound statements, two or more compound statements are logically equivalent. Okay, now for number 2, I will leave that one to you, but the answer is they are still logically equivalent. I think I have already presented it before we discussed logical equivalence, no? The slides before logical equivalence. So they are actually equivalent. So I want you to get or to compare these two, no, to prove that they are logically equivalent. Next, this determine whether the given statements are true. No, in this example, so yan ang gibutang diri nga logically equivalent. So we will just check if this is true, if they are really logically equivalent. Okay, if the two compound statements are logically equivalent. Okay, now I did not place an answer solution for this one, but I believe you already know how to create truth table. So ang inyong buhaton, so what will you do is that create a truth table for the left side and another truth table for this other side. Compare the truth table, now check the combinations. Now if you have P and Q, then not P, then this one, not Q. Check their combinations. If they have the same, for example, no, for this one, you create a table. So not of the disjunction of P and Q. Then the second table will have the conjunction of not P and not Q. Now, so say for example, if not P, now what are the variables that, since these are the given, no mo na itong tanawon nga variables, the combinations of first is P and Q. This one is not P and not Q. Now, for example, on here, I don't know yet the answer. So if the combinations are FF and the result is true, and this one, if we have FF and the result is true, and for all possible combinations, they have the same truth values, but for all lines, no, then they are logically equivalent. So you'll just write, therefore, the two are logically equivalent. I'll just shortcut it because it's. I'll just use shortcut because it's difficult to write using a mouse. Okay, so that's for you to answer. This might be so this might be used, or you might encounter it in our next activities. It can be in your quizzes or in your exam. No? Just be sure. I hope you will solve these items. Now we have laws of logical equivalence. Okay, now what's the use of these laws? These laws are used to simplify compound statements. For example, if we'll go back to the previous slide, this might be simplified further, to a very short statement. No, for example, a compound statement which has 5 atomic statements might be simplified to just 2 or even 1. Okay, 1 atomic statement, and they will just have the same truth values. We have a lot of laws. Now this is the first set. We have commutative. Now when we say commutative, we can exchange the positions, no, of the variables. We can only do that if we have the same logical connective. For example, if it involves 3 variables, now we have P and Q and R. So when we say commutative, since they have the same connectives, then we can interchange them. We can have R, then P, then Q. The result, no, the truth value will be just the same. No, their truth value will be just the same. Now you just have to take note. You can only use commutative if and only if they have the same logical operators or connective. Associative is that we're making use of the grouping symbol, parenthesis. Same with commutative, you should have the same connectives used. No, take note this one. We have conjunctions. Then we can pair Q and R, or we can just pair P and Q, or we can use both commutative. We can have P and R, then we'll group them, then end Q. Okay, that's associative. Then we have distributive. Now distributive can be used when there two atomic statements are enclosed in parentheses, then the other one has a different logical connective. For example, this one, P and Q and the disjunction of Q and R. So when we use distributive, we'll distribute P and the operator N to this, and that will be one group. We'll have P and Q. Then this one will be the middle operator, okay, because we have here another operator, and distribute P and the operator conjunction or connective conjunction. So please do not be confused with operator and the connective, because in later on connectives are just the same with operator. No? Logical operators and logical connectives. Connectives are just commonly used in when statements. No, when we talk, when we write statements. Operators, that's in binary addition, binary subtraction. But anyways, they have the same. They have just the same roles or functions. So again, this is distributive. Now you have to take note of this, the format. So if this is disjunction and the operator enclosed in the parentheses is conjunction, then we can distribute P. Now it can be done the other way around. No, if you are given with this one, say for example, the disjunction of P and Q in conjunction with the disjunction of P and R, so we can simplify this to this. Okay, this longer compound statement can actually be simplified to this form. Okay, that's the beauty of distributive property. Going back. Next is we have identity. For identity, if we are using conjunction and there is a true value, say you already know that the atomic statement is true, then that is just equivalent to the atomic statement P. Now, please do not be confused again also. Now I can use other variables. For example, if I have Q and T, and that is just equal to or equivalent to Q. Okay? Okay. Or I can have if not P or false. This is just equivalent to not P. Okay, so please do not be confused of the variables used. Now P are is just used because it's the most common variable in logic or discrete mathematics. So mamagin niya ito ang ginagamit ng variable. And we also have inverse. The conjunction of P and its negation is false. The disjunction is true. Now because they will for the conjunction, they will always have different values now. You have to take note that in conjunction, for it to be true, for the compound statement to be true, both atomic statements should be true. But here, they will not be equal, no? Because the first atomic statement is just negated by the second atomic statement. However, if we will use disjunction, so it would always be equal to true because at least one of them is true. Next laws, you have double negation. So this is just like multiplication. Negative times negative is positive. Then idempotent. Now, if you get the conjunction of the same conjunction is junction of the same atomic statement, and that's just equivalent to the same atomic statement. Then we have De Morgan. Now, please be careful of this De Morgan. It's just like distributing a negative or a negation, no, a logical and not connective. So when you distribute this negation to the inside the parentheses, now all of them are negated or inverted, including the connective. If you're using disjunction, then when you move this tilde or this negation sign, this connective inside the parentheses, then the operator would be changed. For example, this one, the not of the conjunction of P and Q. So you remove you distribute P, the operator is also affected, and then you negate Q. So that is why we have not P or not Q. Therefore, the negation of the conjunction of P and Q is just logically equivalent to the disjunction of not P and not Q. Same with disjunction. No? Take note that the operator changes when you distribute, when you expand. Okay, when you expand the statement. Then we have universal bound. Okay, when you conjunct any statement with false, that will always be false. When you disjunct any statement with true, and that is always true. And we also have absorption. Now, take note of this. Okay, now this is different with distributive. Why? Because in distributive, you have three different variables. However, in absorption is that you only have two variables. No, this one is P and Q. Here, you have P or Q. Then they are conjuncted to P. So there, the law states that this would always be equal to P. Now, if I put here Q and say R or Q, this is logically equivalent to Q. Okay, that's the second set. We also have the third set of laws, exportation law. So this statement here is just equivalent to here, contrapositive. No, so we have proven this one earlier, that the contrapositive is just logically equivalent to the implication. Then we have reduction ad absurdum. Okay, so we have this one, and equivalence. So the by implication can be expressed in this way or in this manner. So we know that XOR, exclusive OR, is just the negation of equivalence or the by implication. So you have this. XOR is just this statement. You take note of the pattern. So tanawan ninyo, not P or Q conjuncted with P or not Q. So exclusive OR is different. P and not Q is disjuncted with not P and Q. Now, we can rearrange this para mapareha siya sa taas. O, we can have not P and Q or P and not Q. So you check. Oh, pareha sila, but take note of these signs. No, the signs. Take note of the signs. These two are just equivalent. Okay? These two are just equivalent. So, dini lang is wala niya gi-change. Now, from here, nagidiretso lang niya from here to here, butang gi-distribute na negation. So, negative P or not P, then ginat pag yun is P, then the operator changes, then Q becomes not Q, then the operator change or the connective changes from conjunction to disjunction and so on. These are the laws of equivalence. Again, the purpose of this is for us to be able to simplify complex or compound statements which are very long or longer compound statements or complex compound statements. Okay, we have here examples. No, take a look at this one. There are so many atomic many variables involved. So maybe we can simplify these using the connectives. So for now, I have a solution here for number 1. Okay, and I put here the different laws. Now, why I place the law so that I will be guided, know which law I have used. So in your activities, for the preliminary activities, I want you to, when you solve or simplify statements, I want you to indicate what law or laws did you use. For example, here, the quantity of P in disjunction with the quantity of not P conjuncted with Q, the quantity disjuncted with the quantity of P disjuncted with not Q quantity. So, atong tanawon, asa may pili na do mabuhat ani. Now, we cannot combine them using associative nor commutative because they have different operators. Here also, we can use commutative or associative since they have the same operations. Now, pwede na to i-group si P here, but we'll start with this one. This is a very longer compound statement. Now, check the different laws. No, in a quick glance, murag wala. But later, we can find it. No, find a law nga naingon anig dagway. Okay, you have the operators. Just look first for the operators. No, you have disjunction, then conjunction. If you would check distributive, now we can assign this one as our P. This one assign it as a different variable. No, that's because na naman gina si not P. Then we have Q. So therefore, if we will distribute this one, okay, we have P to here. So your result is P or not P. Diba? Then this one, you have P or Q. So you take note, so between aning not P and Q, in between na ron when you use distributive law. So again, here I indicated which law I use when I arrive to that line or that solution. Then using another law, we can simplify this. That's inverse. So this is just equal to true. And another law using identity, this one is just equal to true. Now, as you can see, you now have the same operators, same connectives. So we can use commutative and associative. Now we can group P and P, diba? And Q and not Q because we know that there is an identity nga ang usa ka atomic and its inverse or negation. So, after grouping using commutative and associative, so P or P using idempotent is just equal to P. Q or not Q using inverse is just equal to T. Then again using universal bound and the resultant is just equal to T. Therefore, kanisya, this very long statement is just a tautology. Diba? When I say tautology, for every combination of your atomic statements, the result is always equal to true. The resultant truth value is equal to true. So, ang pinaka-simplified nga statement is this one, T. No, taas kayo siya, but when you simplify it, it's just t. For number 2, so again, same. To study this one, we have the same process. Gapon, we have this, the quantity of P or not Q, quantity in conjunction with the quantity of P or the quantity of not Q in conjunction with Q, quantity, close quantities. Distribute, no? If you think wala na, just recap, review the logical equivalence tables, you will find an answer again. Here, distribute, then this one to here. You will have using distributive law. Kana. Okay, and following these steps, you will get that the simplified statement for this very long statement is just t. For number 3, okay, number 3 uses what I've told you, the distributive law, but using the other side, the longer side, to become a simpler one. Okay, we'll just go first with the first steps. Okay, we have these statements here, these atomic statements here. So you have to use De Morgan first. Since we cannot combine them directly, they have different operators inside. Then we'll have this using De Morgan, then double negation. Next, we can have, so we can group these two. Okay, we can group these two. Since if you recall the precedence, the priority, so unahang ginani mong n, so pwede rin mo i-kuan rin. Now they have the same logical comparators though, logical connectives. Pwede po na mo i-transfer kani siya imong gamiton ani, but it's a different kapoy nagbalhin. As actually you can do that. Now whichever has you think is easier to combine, to simplify, since they have outside the parentheses, they have the same connectives. We're using an conjunction. Okay, then group this using associative. No, I did not use commutative. So when I solve this, I think I can do it just using associative. So if you think you can use commutative, you will be better if you want to transfer this to here, and you can do that. But for me, kana lang, I leave it as is. But I used associative, the parentheses, the grouping symbols. So here, using the reverse distributive law, okay, how did I do this? You have this. Okay, using the reverse distributive law, I arrived to this one. Okay, now, if we recall, we have here P or not P. No, we'll just follow the form in the laws earlier, and we'll combine giunsa na siya nganong nabali. How did I use the distributive law? So if you recall the distributive law, we have P, say or Q and R. Okay, this is equivalent to P and Q, and P or Q and P or R. Okay, muna siya. Now, saan mo na ko ni? Dire. So you have here P or Q and not P or Q. Kung yun yung tanawon dire, in this lower part here, you have not or and or. Now, they have the same connectives, right? However, the difference is just here the letters P are used. No, P is both present in the groups. Here, Q are both present in the groups. So I can rearrange this to Q or P and Q or not P. Diba? Then you can use the reverse distributive law. Therefore, this is equal to Q. So, kani, kopya ko na mo. Q or then you have P and not P. So that is why we have this answer. Okay, so it's just this is the trick, no? We just have to practice and practice para makuha ninyo ang trick on simplifying expressions. And once you are familiar with that, then you can proceed and simplify them. Now, number 3 is just false. No, it's just the logical equivalent to false. Okay, so those are the ways on how to simplify statements, complex compound statements. Okay, now again, I have told you one of the applications of logic is the puzzles, Boolean puzzles, but there are a lot of applications of logic. We have translating English sentences, Boolean searches, logic puzzles, logic gates. So we have, okay, here's a quote from an author: you can access the internet from campus only if you are a computer engineering student or you are not a freshman. Okay, now we can convert this. We can translate English sentences into a mathematical form. No, you can access the internet from campus. Then you can have you are a computer engineering student. Then another is you are not a freshman. Okay, if this is P, this is Q, this is R. Now, since there's a presence of not, then this should be not R. Then you have here only if. So therefore, we will use implication, and another is or, then we will use disjunction. So that's how we translate an English sentence to a mathematical sentence. So the answer will be like this. Now you can let A. No, I used A instead of PQR, but still you can use ABC. Again, I have told you that, well, we don't. It's still all right if you use the alphabets, but you just have to specify. No, for here I specify that A is the first atomic statement, B is the second, or you can use P, the most common P, Q, and R. Then the result will be this one. Now you have A, then B. Now I use a grouping symbol because when I analyze the statement, these two are actually the options. You can access if you are computer engineering. You can also access if you are not a freshman. So that is why I just placed a what do you call a grouping symbol. Though in our rule of precedence, now we can still use this one because in our rule, first priority is evaluating this. Just to make it easier to understand. So again, if you follow the rule, money first priority, then ahiya na dayon ni si implication. Okay, so that's it. That's one of the applications of logic. Also is Boolean searches. Now when you try to search Google, now when you type the words, actually Google is just using Boolean searches. No? For example, if you search, say, Misamis Occidental Universities, so iyan ang gi-search sa Misamis words, mga websites nga na Occidental, mga websites nga na universities. Okay, then iyaran nang gipang or tanan. So that is why na ay manggawas, diba? If you would check your searches na ay dadto nga sa ubos anang search na gawas nga must include university. Kay ang iyang gipang search kay pwede man na Misamis lang na Occidental lang na university lang na, or Misamis Occidental na Now when you specify an and, I want you to try this one. So meaning na It should be Misamis and University, Occidental and University. Ang search. Okay? That's web page searching. Now, web page is just searching the database. The database is the storage wherein you store all of your data. Another is the logic puzzle. Now we have small Yen's puzzle, which was our activity earlier, and the last one is Sudoku. Okay, what I forgot to provide an example for the last one. We have logic circuits. Yeah, so Noni, we will have a different discussion for logic circuits. Okay, that I think that will be one of the lessons in logic. So this will be all. Thank you for watching this video. See you on the next discussion.